Just to step back for a second, we're trying to let you see characteristics that associate an algorithm with a particular class. Constant, linear. We just saw quadratic, which were things like nested loops that lead to that. The next class in that hierarchy are exponential complexity algorithms. These are the most expensive algorithms. And of course, the goal is always, if I can find a solution to a problem that's lower down in the class of complexities, I want to do that. But sometimes, unfortunately, we're going to be stuck with an exponential algorithm. And indeed, many important problems are inherently exponential. There is no more efficient solution than something that's exponential. And that, by the way, is why often when we realize that, we're going to look for approximate solutions, because we may be able to get a good guess more quickly than finding the most accurate guess. A common characteristic to an exponential class algorithm is a recursive function. That is a function that calls itself, but in each call, calls it more than once. You saw an example of that, which was Towers of Hanoi. I remind you, in Towers of Hanoi, we said to move a tower of size n, we move a tower of size n minus 1 to a spare peg, do something, and then move that tower back. So at each reduction of the problem, there were 2 recursive calls. And that's characteristic of something that's exponential class complexity. Let's look at an example. And here's actually a wonderful piece of code. It's very crisp and computes something really interesting very efficiently, or rather does it in a very efficient set of code. The cost is going to be exponential. And the idea is, if I've got a list, say, of numbers, could be the integers 1, 2, 3, and 4, I'd like to generate a list of all the subsets of that list. So what does that mean? The empty list would be a subset. The list of 1 would be a subset. In fact, every list of 1, of 2, of 3, of 4 would be a subset. Lists of 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. You get the idea. So this is going to generate a list of all of the subsets of an initial list. Let's look quickly at the code and then, more importantly, see what the cost is to compute this. So the idea is I set up, as always, a little variable here called res for a result I'm going to return. And then my base case here is if there is nothing in the list, the only subset is the empty list. And I actually return a list of the empty list. Because I remind you, I want to return a list of all possible subsets, and the only possible subset here is, in fact, the empty list. The clever solution, much as we saw with Towers of Hanoi, is to say if I want to generate all of the subsets of a list, what I can do is first generate all the subsets with everything but the last element included. And I do that in a very elegant way. I get the list with everything but the last element, and I recursively call this function. That will give me back a list of all of the subsets of everything but the last element. I then set into extra a list with just the last element. And now I create another list, and for everything in that smaller set, that is all of the solutions without the last element, I also create a solution that includes that last element as part of each one of those earlier elements. It's wonderfully clever. I find a solution to the smaller problem, and then I say for every case where I've got a solution, a subset that doesn't have the last element, I'll also have a version of it with the last element. And I do that by simply running through this loop and adding small, which is the solution without the last element, tagging the last element onto it, and putting it into that new list, which is new. And then finally, I just return every solution without the last element and every solution with the last element. It's a wonderful piece of recursive coding. And in, I don't know what they have here, about 7 lines, I've come up with a great solution to it. Having said all of that, now I just want to look at the complexity. Why is this exponential in size? And let's look at that. So there's my code. I'm going to make an assumption. It's actually a very reasonable assumption that I can do the append operation in constant time. That simply says I need to know where the end of the list is without having to walk down the list, and that in fact happens in Python. So what does the analysis now say? It says that the time that I need is going to include the time to solve the smaller problem plus the time I need to make a copy of all of the elements in the smaller problem. So it's going to be the time I need here plus making the copy right down here of all of the elements in the smaller problem. Okay, so what does that look like? Well, it's important to think about what's the size of the smaller problem. And there I can do a nice piece of analysis. Because I know that in order to solve this for a set of size k, there are 2 to the k possible cases. How do I get that? Well, if I've got k elements, say they're integers, for each integer I can decide, is this one in or not? So for every integer I've got a choice of 2. I've got k of them, so there are 2 to the k possible cases that could be generated as I solve the smaller problem. Now what does that say? It says to solve this case, if I've got n elements in my largest set, I need to solve a problem of size 2 to the n minus 1, all the subsets with n minus 1 elements. I need to solve a problem with 2 to the n minus 2, a problem with 2 to the n minus 3, all the way down to 2 to the 0 or 1 case. And from mathematics, we know that that is, in fact, 2 to the n. And therefore, this is a problem that is exponential. The base is 2, but it grows as 2 to the n. And if you're a little confused about how bad is it to compare n squared to 2 to the n, try some examples. You'll see that the exponential one grows much more rapidly than the quadratic one. And the characteristic here is I'm breaking this down into sub-problems that I have to call multiple times, just as we saw in the Towers of Hanoi case. So there's a nice characteristic of an exponential complexity algorithm. That now has let us have a run-through of the things we've seen. And I'll simply remind you very quickly. Constant time is just doing a set of operations. There could be a recursive call in there, but it's going to be constant no matter what the size of the problem is. Logarithmic, I'm breaking the problem in half or in portions as quickly as I can. And we want to use that idea when we think about things like bisection search. Linear, we've already seen it could be just a loop that I'm going through some number of times, the number of times being a reflection of the size of the problem, or something that recursively calls itself, as in factorial, again, a number of times based on the size of the problem. Polynomial, again, we've already seen examples of that, recursive calls being very clear examples. And exponential, characterized by having a recursive calls, but where we're breaking the problem down into multiple calls each time around. And as I said with polynomial, the most common one here is where c is equal to 2, and a great characteristic of that is nested loops.